Today, in this video, we are going to discuss about the concept of magnetic field produced by a current carrying conductor. A current carrying conductor produces a magnetic field when it is placed in an external magnetic field. Two magnetic fields will interact, it will exert force. So, a current carrying conductor experiences force when it is placed in a external magnetic field. So, first we will see how a current carrying conductor produces a magnetic field. What is its direction? What is its value? We will discuss in detail. First we will see the direction of magnetic field. Afterwards we will see what is the direction of magnetic force. Afterwards we will see magnitude of magnetic field produced by a current carrying conductor. Okay. If any conductor is carrying current in this direction, this current carrying conductor produces magnetic field around it. If it is a current carrying conductor, it produces magnetic field around it. Magnetic field lines are closed loops. Electric field lines are open loops. See, remember, in competitive examinations it is important. Conservative electric field. Conservative electric field, that means a field produced by a charge is conservative electric field. Conservative electric fields are open loops, but non-conservative electric fields are closed loops. Remember, they are similar to magnetic field lines. Don't confuse with this. Electric field lines are open loops, means conservative electric field. Closed loops means non-conservative electric field. Magnetic field is always closed loop. There is no confusion in this. Remember this important. Non-conservative fields we will discuss later. So this current carrying conductor is going to produce magnetic field around the conductor. Okay. So the direction of magnetic field produced by a current carrying conductor can be known by using right hand thumb rule. Thumb indicates the direction of flow of current. Curling fingers indicates the direction of magnetic field. See, if you imagine this piece of chalk is a current carrying conductor carrying current upward, then the thumb will be arranged like this. These curling fingers are going to represent magnetic field line. Magnetic field is a vector. The direction of magnetic field can be known by drawing tangent to a magnetic field line. Okay, here you imagine this is a magnetic field line. Here field is in this direction. Here field is in this direction. Here field is in this direction. Here field is towards you. Here it is inclined. A tangent. We should draw a tangent here. So for this current carrying conductor, this side magnetic field is into, it goes into, and it will come out like this. It will come out here. Here magnetic field is into the board. Here magnetic field is out of the board. So this is, I am going to represent one magnetic field line going into, coming out. This is another field line going into, coming out. This is another field line going into, coming out. This is the magnetic field produced by this small portion of the conductor. These field lines are circular in plane. Okay. So this is how the magnetic field is produced by this conductor. But now we are not going to focus on magnetic field. We are going to focus on force acts on this current carrying conductor when it is placed in an external magnetic field. That we will see now first. This is very important derivation for board examination. They may ask for 3-mark question. So it is a board question. Follow very carefully. See here, the external magnetic field is into the board. Into the board. If you place a current carrying conductor carries current I, usually here this current carrying conductor have certain length. If I take small portion of the length dl, then IDL is called I into dl is called current element. current element, it is a vector, dl is a vector, so il becomes vector, current element becomes vector, current unit is ampere, dl unit is meter, so unit is ampere meter. But in this case, the angle between length and magnetic field is 90 degree. So that's why I am not going to use this diagram. I am going to apply magnetic field in this direction. Magnetic field is in this direction B, and I will take conductor in this direction, current carrying conductor in this direction. Then angle between magnetic field and dl will be theta. It makes certain angle. Already we know force acting on a charged particle when it is in a uniform magnetic field, that is Q into V bar cross B bar. Now to calculate force on this conductor, first I need to know how much total charge lying in this conductor. That I have to calculate and I have to substitute here. Then I will get magnetic force acts on this conductor. For that I am drawing conductor in a different way. This is a current carrying conductor of length L, area of cross section is A. We are going to take one small unit volume inside. In this unit volume we have number of free electrons. Number of free electrons are represented with letter N. This small n is a number density. Number of free electrons present in this volume is called number density. Okay, if n number of free electrons are there in this volume, then number of free electrons in the conductor, number of free electrons, capital N can be written as small n into volume. This is number density into volume, gives you number. So total number of free electrons is n into A into L. Area of cross section into length gives you volume of the conductor. Okay, charge of the electron is E. Total charge Q becomes n into A into L into E. L into E. This is the total charge. Okay, but in this conductor, electrons are going to move in a random motion. They'll move in a random motion, but the displacement of this electron from one end to other end is going to represented with drift velocity. That is going to represent with drift velocity. This is very, very, very important. See, inside the conductor, electron may moves with a speed equal to 10 to the power of 5 meters per second or 10 to the power of 6 meters per second. Like that, the electron moves very fast inside. But when after some time electron begins here, it ends here, then it displaces only this much. This is the displacement of the electron. But original path is a very long distance. Okay, to travel from here to here it may take t time, but length of the electron traveled is huge, but it is drifted from here to here. So this is the drift length. So distance divided by time gives you drift velocity. Drift velocity is different, velocity of the electron is different. So that means inside current is flowing means current is flowing in this direction means electrons are flowing in this direction. It takes some time to travel from end B to end A. This is the distance L. To travel this distance, electrons take certain time. That time, distance divided by time gives you drift velocity. So that's why this is the total charge present. So magnetic force is equal to total charge present in this conductor is N A L into E into velocity of the charged particle is this. This can be represented with drift velocity into applied magnetic field. Now from current electricity, current I is equal to NEAVD. So that's why this NEAVD can be written as current. Current is a scalar physical quantity, so that's why it can be brought outside. So magnetic force F is equal to I into this L is length of the conductor. This length of the conductor is a vector. Length of the conductor is a vector. So that length of the conductor is taken inside. So it becomes L bar cross B bar. So this is the expression for magnetic force acts on a current carrying conductor when it is placed in an external magnetic field. It is a vector form and magnitude form, scalar form is F is equal to I into L bar cross B bar can be written as LB sin theta. Okay, this is magnetic force in scalar form. Magnetic force is ILB sin theta. Magnetic force is ILB sin theta. This is very. See, we are going to see some very important applications. For example, if the magnetic field is into the board, a current carrying conductor is placed here. This current carrying conductor produces into field here, outfield here. This produces field, external magnetic field is there. These two will interact. So this current carrying conductor experiences force. That magnitude of force, scalar form, can be written as ILB sin theta. Theta is the angle between L and B. In this case, angle between L and B is 90 degrees because B is into the board, 90 degrees. So magnetic force is maximum, that is ILB. But force is a vector. We need to know direction of force. The direction of force acting on a current carrying conductor can be known by using Fleming's left hand rule. Here magnetic field is into the board, current is flowing in this direction, so magnetic force acts upward. Okay, in this case length of the conductor is same as length taken. Length of the conductor and length of this both are same. But when this conductor is bent in the form of a semicircle, loop, it is carrying current in this direction. Even now, every portion of the conductor is perpendicular to magnetic field. So magnetic force is maximum only, but it carries current I, so I have written. We have placed in an external magnetic field B. Theta is 90, sin 90 is 1, but this L is going to be vector. This is a vector, L is vector. So whenever a length of the conductor is an arc, or length of the conductor is a zigzag like this, if it is not a straight, even though if it carries current I, we should not take this entire length. This is distance, but we should take effective distance, effective length. That means displacement. Distance is a scalar, displacement is a vector. So we need to take the shortest length of the conductor. That means we have to join a straight line joining between the ends of the conductor. We should join like this. See here, this L length of the conductor is bent in the form of a semicircle. So effective length is this. For this, we can call it as radius of this semicircular arc. This is radius of the semicircular arc. So that's why this length is going to represent with 2R, not with this L. Okay, this is the answer. If this answer is not there, magnetic force is expressed in terms of length of the conductor, then we know length of the conductor is half of the circumference of the circle. So L is equal to pi r. So from this we'll get r. R is L by pi. So magnetic force becomes Fm is equal to I into 2 times L by pi into B. Now this is the magnetic force acting on this section. If we want to calculate this section, if it is L is the length of the conductor, but this distance we don't know, so we will take it as x, then magnetic force Fm is equal to I into x into B. I into x into B. To calculate this x, we need known geometry. If that known geometry is there, I can calculate successfully the shortest distance between the two ends of the conductor. That I'll substitute it here. If this length of the conductor is bent in the form of a semicircular arc, bent in the form of some awkward shape, but if it is bent in the form of a circular loop, if it is bent in the form of a circular loop, current is flowing in this direction. Current is flowing in this direction. Okay, but here this is the initial point, that is only the final point. So there is no distance between initial point and final point. Initial point and final point displacement is 0. So that's why effective length is 0. Effective length is 0 means magnetic force M is equal to I into 0 into B. So magnetic force you will get it 0. Here on this circular loop, magnetic force is 0. Why this is magnetic force 0? We will see carefully here. If we take small elemental portion here, magnetic field is into the board, current is going down, so magnetic force will act in this direction. Similarly, I am going to get same elemental portion here. Here field is into, current is going upward, magnetic force acts in this direction. These two magnetic forces cancels. This force tries to take this loop in this side. This force is trying to take this loop in this side. These two are equal and opposite, cancel. Similarly, here if we take elemental portion, here field is into, current is in this direction, force will act upward. Here force will act downward. Here, the magnetic forces will act radially outwards from the circular loop. So that's why net force is 0. So this magnetic force increases the tension in the ring. If at all it is a soft material, its radius increases. If it is a stiff material like a metal wire, radius may not increase, but tension increases.